Okay, so this is work by Perez, working on NASA Ames, and Ángel Herranz, which is one of the authors in my previous talk. So Ángel couldn't be here, has a lot of paper working in Madrid right now. So he asked me to present this because this is a good place, as you have seen, to discuss the connection between logic programming and functional programming, right? Okay, so here we are. Sorry for the spoiler. Okay, so basically this is just another take on this topic on either embedding logic programming in Haskell or the other way around, right? So in this case, there's a different motivation because they're actually using Haskell for some projects at NASA. And, well, they realized that for certain libraries, they would be interested in adding some deductive capabilities to the existing functional code, right? Which is good for us. So when Ivan approached us, we told them, okay, you have basically two possibilities. One is the interlanguage interfacing. So try to think about one interface between Haskell and Prolog and so on. Or the other possibility is use Curry, which is a wonderful programming language and is the future of functional and logic programming. But for whatever reason, they were not happy to change existing code. I mean, for instance, you can think that they're using a very specific Haskell environment and very specific Haskell libraries. So it's not that easy to introduce this connection between different languages. So they have decided to embed some part of logic programming inside Haskell. So they used, basically what they did was to apply some solution that worked for an existing Haskell library that they use to this problem. And this is kind of problem transformation that is this Extensible Types library. And they have used this to extend existing algebra data types with variables. So there's a generic construction that adds symbolic atoms to existing data. So it's not a new idea. There have been semantics of functional logic programs that use this idea of extending algebraic data types with special atoms and so on. So basically, this is what they do. They use problem transformation. They have defined a combinator DSL for conjunction, aggregators, and so on. And in the end, they prove that more or less this Haskell library can do basic logic and constraint programming without exiting Haskell. So we don't know the actual implications of this. This is the work in progress, how to assign a semantics to some of the constructions. But it is nice, and we thought it would be a nice proposal for you to know how they did it. Okay, so this is an actual Haskell code with a logic programming query using their technique. So there you have an algebra data type for defining piano naturals, right? And that would be the definition, the standard Perl definition of lesser or equal comparison operator in Perl, more or less, with two clauses, right? So x is lesser or equal than y if x is 0, or if both are different to 0, and x is the successor of x1, y is the successor of y1, and x1 is lesser or equal than y1. Okay, that's very basic logic programming. So what they do is that they define a new Haskell function that goes from, not from naturals, but from terms of naturals and terms of naturals into logic programming goals, right? Not booleans, but goals. And this is the actual definition of this using the embedded DSL, right? So there's some sugar here, but it's more or less real. So you apply exist to a function that takes two things, and you have these two cases. So this is a disjunction combinator. Either x is 0 or x is the successor of x prime, This is a conjunction combinator. Y is the successor of y prime, and x prime is less or equal than y prime. So basically, you can read this Haskell code like you read Prolog code, and you can call this Haskell find all function, find all the x, that x is less or equal than 2, and you obtain this list. So more like it works. In the technical report, there are more elaborated examples. There's even a Sudoku written with the library, and it works as expected. So how do they do this? Well, basically, they make this problem transformation that traverses type definitions and is very generic, and was presented in a previous work by Ivan on this design pattern. So you start with an algebraic data type, and you obtain something that's kind of a homomorphism, a type of homomorphism, where you apply a function below each functor, right? So from natural, you obtain nat f that expects some f. So you have 0f and successor f, capital F, and it's applied to f applied to natural f of f. So this is from these you obtain this new data definition. This is a generic construct that you can do for every type that you have. And this is important because they're specifically interested in logical programming with types. So they don't buy these flexible types motive for not using Haskell. They want the types from Haskell, but they want the didactic capabilities in Horcruxes, right? So they are very happy that there are types here. So from this, we define the term construction. Well, term is a type constructor that for any type can be either a variable with a name or a compound of that type. So when you apply the transformation to a given type using term, you obtain, in this case, the terms of type nat, which is term of nat f term. Okay, so this can seem a bit tricky, but it works. So in the end, there is a library that performs this at compile time by program transformation, and there is also some desugaring. So in the end, from the x variable in Prolog, you would obtain the nat term term v of x, but you can desugar this, you can sugar this, so you don't have to write the v. So the v is erased, and the user just inputs the quote x and so on. So you can desugar things. So in the internal representation is this nat term representation, but the user just writes the variables in quotes, so it's more readable, right? And there are some combinators for manipulating the goals. So succeed and fail are like the true and fail in Prolog. We have the disjunction combinator that we saw before, the conjunction combinator that takes two goals and returns another goal, another Prolog goal, and this equality and unification operator that takes two terms, two polymorphic terms, and return a goal, right? And with this, you can compose any logic program, right? We also have existential quantification. There's even a cut. Of course, I don't like cuts, but they have implemented a cut. It's not based on backtracking. I think it's based on collecting a frontier semantics, but they have implemented the cut. And some aggregator operators. So if you're interested in this, there are a couple of papers that I will reference in the next slide. So far, they have managed to implement several things. So for future work, I will be part of that future work because I have some experience with semantics. We don't know what this means in general because we don't know how the functional features in Haskell are going to affect some examples and so on. And the prototype is quite slow, as you can imagine, because there's no an abstract machine executing this code, but it's basically an interpreter, right? Of course, you can improve that with partial validators and so on, but this is in a very early stage, if you want. There are also some examples where they are starting to introduce solvers for constraint logic programming in a very early stage. So these are the two papers, if you're interested in the technique. This logic programming with extensible types, and the previous work on this design pattern of extensible types by program transformation. That's it. Thank you.
So I noticed that you use sort of ground representation for terms, so you don't have actual variables. And then from when I work on partial evaluation, I remember that then implementing a unification was very, very expensive. So do you know if they have problems with this, scalability problems?
A well-optimized unification routine, yeah. So it's at the moment this is very inefficient, of course.
Variables, then perhaps it's not possible or goes against the idea of what you're doing. So
have taken this path, right? But once that someone working in Ames research has taken this path, I think it's interesting to discover what are the limitations. Perhaps one of the conclusions is that it's mindless to follow this path. But maybe there's some workaround, and by using functional programming optimizations, you can get something that is surprisingly okay for some examples. We don't know. So this is very exploratory. So this is why I think it is okay to be in the hands of somebody with a lot of experience on functional programming optimization. This gets better, right? But it's crazy. It's a bit crazy, I think.
You mentioned the motivation was that they have also some Prolog code and do not write them new. So what is the idea if here they have a different syntax? It should be
no. The motivation is because they have code that is already written in Haskell, and that has been tested a lot. And for instance, if they embark it on some probe, it's very tested, and they want to keep only one runtime environment for one language. They're not going to embed a Prolog implementation.
Okay.
That kind of limitation. So it's a very extreme restriction. I mean, it's not like for general purpose, I prefer covering them. Okay, I can buy that, but they have a particular limitation because these libraries have been developed for 10 years or so, and they don't want to change anything.
But these are then the Haskell libraries, and then they just want to add some Prolog code.
They don't want the interfacing problem because they want to be sure that there's no mistake in translating a Haskell data type into a Prolog data type, this kind of thing. So they work with very limited execution environments.
So going back to that motivation question, and I mean, I think we're probably all in agreement of this is maybe not the way we would choose to do it. But do they know there's a query compiler that actually generates Haskell code? And if they want to interface with, they could like write their query code, have the generated Haskell code, and then interface with that. Okay. I'm just saying that is technically an avenue. I don't know like how much people want to interface with generated code, but it is technically an avenue.